This is just a little bit more detail on looking at transient impacts or time-dependent impacts. We often talk about horizons of 2100 or the last 2 decades or 2050 and so on. But obviously the impacts of climate change evolve over time, especially with all the scenarios also evolving over time with certain trajectories, certain rates, and so on. And the models take the scenarios and produce rate of change of climate change, which translates to impacts, time-dependent impacts. So this is one example of water withdrawal and water stress that is expected. This paper argued that a previous report that had argued for a certain level of water stress was an underestimation. So they are basically extrapolating the data on population, water withdrawal, and GDP growth pro capita. They keep calling it pro capita basically because I think they extrapolated it. And they're looking at the whole world and individual countries that are already facing severe water problems like Pakistan, India, Bangladesh, Angola, Malawi, and Uganda. And they schematically show scenarios where the demand and availability can be basically linear, or they can be non-linear and can lead to water crisis when both are so available. Clean water available is dropping non-linearly, and the demand is increasing non-linearly to hit a point of water crisis at some time horizon. So these are kind of extrapolations, so one has to be careful. But when one looks at what the exploitation of global freshwater for agriculture, industrial, and domestic uses have been, in aggregated regions in trillion meter cubes of water. This is the Organization for Economic Cooperation and Development, which has increased over time. BRICS, Brazil, Russia, India, China, South Africa, have all been economically growing, and their demand is grown quite substantially, especially during the Green Revolution and thereafter. So this is a combination of increased food production, increased population, increased industrial activities, and so on. And this is the rest of the world. So this does seem like there is no end to the exploitation of freshwater resources. When one looks at the models in terms of increased exposure to water resource stress by 2050 and decreased exposure to water resource stress, and this is increased exposure to river flood risk and decreased exposure to river flood risk. I'm showing this basically because there are the scenarios done here for with RCP and SSP combination. So RCP 2.6 and the 5 shared socio-economic pathways, and other RCPs as well with the shared socio-economic pathways. And these are the models that participated in CMIP 5. And the point I would make is that all of them indicate some sort of an increase, but the range for each scenario is quite significant. So one has to take this into account, that model estimates of water stress increase and decrease in terms of millions of people for the same scenarios can be quite large. The difference here from 500 million people to 3 billion is quite large, significant. Same for increased exposure to river flood risk and decreased exposure to this one is much closer. I suspect the precipitation projections that we looked at, where there are many regions that the models don't have a good consensus on as opposed to temperature, translate to the other calculations going into water resource stress and river flood risk as well. So land use modeling details, vegetation model details, and all sorts of parameters obviously play into these. But as I said, decisions still have to be made under these uncertainties. We can't run away from them in any ways. Looking at CO2 emissions in concentrations, anthropogenic radiative forcing, and global mean temperatures going into the from the historic period into the 21st century. This is showing CO2 emissions for various scenarios. So RCP, SSP, combinations again, and you can see again the range in terms of CO2 gigaton total gigaton CO2 is also quite large. Obviously, for these scenarios, it's critical to make sure that we know the uncertainties, because these are our safest bets in terms of keeping global warming to less than 2 degrees. When you convert them to CO2 concentrations, as well as we talked before, there is a large range here. This is the total anthropogenic radiative forcing resulting from that. So even when you have RCP 2.6, you are giving it a concentration pathway, representative concentration pathway. That's what RCP is. A model's radiative imbalance need not be 2.6 exactly. That's a mean over many calculations, and also includes the integrated assessment model input there. So the point is that the time evolution of the impacts is going to depend on redoing these along the way and calibrating with respect to the historic period. So you can see here are the historic periods, and those are the ranges. So temperature range, as we have seen, obviously the benign ones are down here and the business as usual scenarios are up here. When you translate that into changes in cropland, forest land, pasture, and other natural land, you obviously end up with various ranges of changes. So some of obviously RCP, I don't know why RCP 4.5 for example is showing a decrease here, a massive decrease in the cropland area, but many are showing decrease in forests, and some are showing increases. Okay, so the same with pasture and other natural lands. Okay, so time evolution of the impacts is important, but there seem to be several uncertainties, or at least differences in the model projections when it comes to critical issues of water stress and changes in land use like croplands, forests, and so on. They are all related to each other. Obviously, water is related to precipitation projections, which have large uncertainties, and that results in estimations of cropland and forest use and so on. Even though forest land is one of the key parameters to keep the carbon sinks going into the future. It's a big part of the Paris Agreement as well, in terms of countries promising to do more afforestation as well as reduce deforestation and forest degradation. Okay, so obviously we have to deal with the models as they are and hope that the time evolution of the impacts will keep getting calibrated, and uncertainties or the range of very intermodal variability will be made more narrow, maybe somehow more reliable. And then you have to worry about these being accurate at regional and local level for adaptation issues. So obviously a big challenge. Let me add a little bit to this podcast on recent trends as well, looking at crops. We're talking about time varying impacts, time evolving impacts. So this is a study of synthesizing various published studies looking at wheat, soy, rice, and maize in terms of the yield losses projected or detected, projected with percentage per decade for these 4 crops. So the number of estimates from these studies, which showed the range of reductions per decade of -10 to -5, -5 to -2.5, and some showing no significant change versus some showing an increase in yield is shown here, with a lot of them concentrating on a change of 0 to -2.5. Of course, the spatial variability of the change also matters. For example, if a country that's already having food insecurities gets hit with these yield changes, then that's going to be much more severe than for a country which is doing very well. We have to also keep in mind what we said before, that the tropics, which are already warm, are going to suffer more than the temperate regions where warming may in fact increase the yield. So the regions matter as well for climate trend impact on yield. So this is different kinds of models, statistical model and process model. They show very different range of yield losses as well. Most of them are in the negative range, but this one has a tail that goes into the positive as well. These also have a small 90th percentile range in the positive side. Some models considered CO2 increase, some didn't. So you can see that including CO2 increase increases the negative impact on yield per decade, and wheat has a larger drop than soy, which seems to be robust here, with some potential for positive yield impact. Rice mostly negative, but somehow more robust than wheat, and maize is over here. You can also see these in terms of the potential for increasing the yield and decreasing yield with time. So if you look at the percentage of yield projections, most of them are positive and negative in the near decades. So there are many projections that are positive and there are many that are negative. And as you go in forward in time and the warming gets stronger and stronger, almost all of them begin to just project negative yield changes. So the positive yield change begins to drop off in the future. So the model consensus in that sense is increasing into the future, that with continued warming beyond a certain threshold, we are going to mostly have decreased yield across all crops and across the globe. So in that case, still the pattern of decrease matters, but the loss is going to affect global food markets, and especially if the projections are depending on bioenergy, then that competition for food grains versus bioenergy demand is going to matter. And this has already played out during some severe droughts, I think in 2011 in the US, when the crop yields dropped massively, and then there was a massive competition for ethanol, livestock food demand, and consumption by human beings. So it's not something that can be taken lightly, but decreasing yield is always a concern anyways.